Hello everybody, my name is Diego Arcos Avilés of Universidad de las Fuerzas Armadas de ESPE from Ecuador. I am going to present the paper entitled Energy Management System for an Isolated Microgrid Based on Physiologic Control and Meta-heuristic Algorithm. This is a collaboration work between Universidad de las Fuerzas Armadas ESPE and Catholic University of Leuven. I want to thank the Flemish Inter-University Council and the Belgium Development Cooperation for supporting the project Mira-Este, which is developed between Universidad de las Fuerzas Armadas, ESPE, and KU Leuven. This is the outline of this presentation. First, I will present a brief introduction to the topic under study. Next, I will describe the isolated microgrid scenario under analysis. Then, I will present the design of the physiologic energy management system, and I will present the procedure to follow it to adjust the physiologic control parameters. Then I will show some simulation results, and finally I will present the conclusions of this study. As is known to all, there is a global concern related to reducing the existing gap in access to electricity, especially in isolated areas, to improve the people's quality of life. The use of fossil fuels to supply energy is quite common in this scenario, considering that a diesel generator is easily accessible and facilitates the sizing of an electricity generation system. However, several studies continue to reduce as much as possible the environmental pollution produced by this type of generator, especially for the greenhouse gases that they produce when operating. For this reason, several studies have focused on the design of hybrid power generation systems that combine diesel generators with renewable energy source. Some studies in Ecuador discuss the use of this hybrid power generation system focus on areas where there is no electricity. This is because increasing electricity access coverage becomes a complex issue in Ecuador due to the geographical conditions. Despite the efforts made, there is still a great potential for hybrid power generation system studies that have not been fully exploited in this country. Also, the sizing of an electric generation system varies depending on its geographical location, directly affecting the appropriate use of renewable energy source and the system environmental impact. So, this paper aims to generate a new, viable, and sustainable solution to improve access to electricity in isolated areas. Therefore, this study proposed the fuzzy-based energy management system designed to improve the efficiency of an isolated microgrid located in Ecuador. In this study, the parameters of the fuzzy logic controls are adjusted using two meta-heuristic algorithms, namely QQ search and particle swarm optimization. Here in this slide, we can see the microgrid considered in this study, which comprise a diesel generator, a photovoltaic system, and lithium-ion battery energy storage system to satisfy the community demand located in Ecuador. In this figure, the direction of the arrows implies a positive power flow, so the generation and load powers are always positive, whereas the battery power is positive for battery discharging and negative for battery charging. Here we can see the block diagram of the proposed fuzzy-based energy management system that comprises 5 blocks. And with these blocks, we provide the reference values of the photovoltaic generator, diesel generator, battery storage, energy storage system, and the diesel generator status indicator. The block 1 consists of a moving average filter in charge of computing the average of the forecast generation and load data to have prior knowledge of the amount of photovoltaic power that the system could use to cover the demand. Block 2 performs a state change at diesel generation startup and shutdown by considering a minimum startup and shutdown times to reduce fossil fuel consumption and try to closer to an actual operation. This way, when the control strategy requires power from the diesel generator, the energy management system must turn on the diesel generator for at least 2 straight hours, then keep it off for at least 2 hours. Consequently, it reduces the cost generated by each generator start up and avoids an start up immediately after it is off, or vice versa. Block 3 computes the power delivered by the battery energy storage system. The battery power reference value is defined as the difference between the load and the available power generation. In addition, this block determines if the battery is in charging or discharging mode, considering restrictions to avoid deep discharge or overcharge at each sample. Block 4 performs an estimation of the current battery state of charge value based on the battery power. Block 5 decides the value assigned to the physiologic control output based on the forecast data, the previous battery power, which is in the information concerning the system dynamics, and the estimated battery state of charge value. The physiologic controller is designed to keep the battery state of charge within the maximum operating limits, properly harnessing the solar resources, satisfying the demand at all times, and minimizing the diesel generation consumption. The physiologic control assumes a Mandami-based inference, a center of area-based diffusification process, and uses 3 inputs and 2 outputs. Each input and output has 5 membership functions. Therefore, the FUSI rule base comprises 125 rules to cover all possible scenarios in which the microgrid can operate. This study used an offline adjustment of the FUSI logic control parameters through meta-heuristic algorithms to minimize as much as possible the performance metrics and try to bring the system to a better solution. Cuckoo search and particle sum optimization algorithms are used in this study. This figure shows a uniform distribution of the membership function for the 2 outputs of the FUSI logic control before parameter adjustment. In this figure, the circles enclosing the membership function vertices correspond to the parameters that the meta-heuristic algorithms will adjust. Conversely, the squares at the corners are those parameters that will remain fixed and will not be modified to keep the relationship between the boundaries of the universe of discourse and the rule base. Each membership function belonging to the FUSI logic set PS, PM, and PMM has 3 adjustable parameters. In addition, the FUSI subsets 0 and PB have only 1 adjustable parameter. Therefore, the meta-heuristic algorithms will adjust 22 parameters, 11 for each output. The optimization problem is formulated as multi-objective by using the weighted sum method, considering 3 restrictions: to avoid crossing the limits of the universe of discourse, second, to avoid modifying the shape of the triangular membership functions, and third, to avoid inconsistency when finding the FUSI control solution. This is the cost function that considers the reference value of the battery state of charge limits, the reference values of the total price of fuel consumption, the reference values of the power losses by the generation source, and the objective function that tries to keep the battery state of charge oscillating close to the 60% of the battery charge. Here we can see the resulting membership functions for both FUSI logic control outputs after their adjustment. In dashed lines, we can see that the original membership function, and in solid lines, the resulting membership function after parameter adjustment for both methods. Now I want to present some simulation results. This figure shows the convergence of the optimization algorithms while finding the best solution over the 300 iterations performed. We can see that the particle swarm optimization presents a further convergence than the QQ search algorithm. In addition, this table presents the best results obtained in the performance metrics when evaluating the proposed energy management system, the energy management system adjusted by the QQ search algorithm, and the energy management system adjusted by the particle swarm optimization algorithm. We can see that using parameter adjustment in the proposed energy management system, the number of hours that the battery state of charge remained at its lower limit decreases. In addition, with the application of both optimization algorithms, the cost generated by fossil fuels is reduced and the photovoltaic generator losses are minimized. Here we can see the resulting profiles of load photovoltaic power, diesel generator, battery power, and battery state of charge, resulting after applying the energy management system adjusted by QQ search algorithms for 2 consecutive days. Here we can see the same, but for the energy management system adjusted by the particle swarm optimization. Both results imply that the battery life is extended by controlling the battery state of charge from reaching its limits. Now the conclusion of this work. I have presented the design of a FUSI-based energy management system for an isolated microgrid comprising photovoltaic and diesel generator and battery energy storage system. The proposed system has been developed with the purpose of supply electricity to an isolated community in Ecuador. The control strategy has considered constraints on diesel generator startup and shutdown, satisfy the demand at all times, took advantage of the available solar resource, and maintained the battery state of charge value within safe limits. The proposed energy management system used a FUSI logic control block to compute the power required by the diesel generator and the photovoltaic system. The parameters of the FUSI logic-based energy management system have been adjusted using 2 meta-heuristic algorithms, namely QQ search and particle swarm optimization. It has been demonstrated that the FUSI energy management system adjusted by the particle swarm optimization algorithms present improved results regarding QQ search algorithms. Future work will focus on performing experimental validation using accurate load data, actual variations in the diesel generator output power, and considering potential errors in the state of charge predictions on the battery system. Also, applying the proposed energy management system in a set of multiple interconnected isolated microgrids to exchange excess energy in each microgrid and improve the overall efficiency of the entire system. Thank you very much for your attention. If you have any question, don't hesitate to contact me.